Here's 7-1. I'm just going to do a single day. Just to kind of put it in context, think about it with section 2. Solving systems of equations is going to be the name of the game. Really the only difference in the two sections is going to be the method that we use. Okay? Everything today in section 1 is going to be substitution, and everything in section 2 is going to follow a method called elimination. You can kind of take, I mean, this is really just something for you to refer back to if you need to, because my guess is with the steps to use substitution, you'll go off of the examples and kind of refer to those for other problems in the future that you may not be sure how to do. You can break it down into 4 steps. You solve one of your 2 equations for a variable, plug it into the other one, solve, and then substitute in the value that you know. Okay? Now you may, without seeing an example, you may see that and you're like, sure, whatever. I'm not exactly what that looks like in the context of a problem, but again, think of this slide as if you want to, review kind of the 4 technical steps to doing substitution, there they are. All right, here we are with our first one. Now, let me just say one thing to kind of, because you may come to this back to this example in the future and be like, with these 2 methods that we have, isn't this really more of an elimination than a substitution? With some examples in this first section, you might eventually feel that way about them, but that's not really a thing right now because today is all substitution. All right, so very, very first thing I'm going to do is if I subtract x from both sides, this first equation would be y equals 4 minus x. Okay? And now, here's where the technique really gets its name, is I have a y here, and notice I have a y there. Okay? The problem with this second equation is I can't solve it because it has 2 variables. But if I substitute, and I say I'm going to take y out, and I'm going to put 4 minus x in, now that equation only has 1 variable, which is x. I can distribute this negative sign. It doesn't leave us with a really terrible equation to solve. The x's can be combined into like terms. There's 2x. And then if I add 4 to both sides, I get 6. Divide by 2, and I get that x is 3. Okay? But this system of 2 equations had 2 variables, so that's just half the story. I need to go back and to get y. Right? But you'll see here, once you have that first one, you've really done the toughest stuff. You can go back up to either equation. I'm going to go here. This is a totally different situation now because I know that x is 3. And so y would be 1. Okay? There really is, that's kind of the way, because in this chapter we're going to cover sections 1 and 2 and then jump over and do 5 and 6. We're not going to do 3 and 4. So really what's going on here is in the first 2 we're taking the algebra approach to solving systems of equations. And then in 5 and 6 we get to the graphical approach. Now I do want to mention though, in terms of a graph, kind of what's going on. Again, we're really not going to get into that yet, but I think it's just worth noting. Okay, these 2 equations were both lines. My graph is not going to be accurate at all, which is okay. One of the lines had a positive slope, the other had a negative slope. I don't really care at all about the accuracy. What I do want to point out is if we plotted both of these on an XY coordinate grid, the coordinate point 3, 1 is where those two lines would intersect. Okay? It's not gonna, you'll kind of on specific examples, you'll see me come back to this and just kind of refer to it that, you know, think in terms of sections 5 and 6. I'm trying to kind of lay some groundwork here for the graphing stuff that we're going to get to later on. But that's a big connection with these systems of equations, that when we find these solutions, that's where the two graphs would intersect if we were to graph them. All right. Let's tweak this one a little bit. Here's example 2. Okay. Now this one's a little tricky because we have to write the equations. That's not going to be the case on all of them, but some of them it will. Okay, so this description gives you an amount of money that was invested into two accounts. I'm going to say that my x variable was the amount invested at 5%, which would therefore make y the amount invested at 3%. Okay, some problems may define, like if it's a word problem, they may define your variables for you, others may not. If they don't, it is important that you do. Okay, you need to be clear what's what, because the next thing I want to do is to go solve for x and y. So I've got these two variables, and the equations that I'll set up really will reflect that the information given tells us two things about the problem. Number one, x plus y have to be 12,000. That's how much money was. That's how much money was invested. Now it tells us in terms of interest that the accounts together in a year earned $500. So if I were to take 5% that was invested in account X and 3% that was invested in account Y, that has to be 500. Okay? Two equations, two variables. All right? Remember, the first part of substitution is always, I'm going to start with this first one because it's just easier to solve, is one of the two equations has to be solved for one of the two variables. Okay? So I took the first equation and I solved it for y. And when I say solve, I don't mean that I have a number for it, because I don't. And I won't for several steps. When I say I solved it for y, I moved all the other terms to get y on one side of the equation by itself. That's what I'm referring to. Okay? Because now what I can do on my second equation is I have 0.05x. This step right here should feel somewhat similar to the first one. Okay? That we make the substitution. Y is out, and then 12,000 minus x is in. And at this point, my whole focus is on that expression that I have, because it's a single equation with a single variable, which means we can just use inverse operations to solve for it. So I distributed the 0.03. Let's see, there's two terms here with x's. Those are like terms. So I'll say I've got 0.02x if I combine them. Then I should subtract 360. I get 140. Divide by 0.02, and x is 7,000. Okay? And if I were to go right back up to here and plug in 7,000, you can just, the numbers are nice enough that you might be able to just do it in your head. That would mean the amount invested in Y has got to be 5,000. All right. Here's what's going on here. This one I actually want to illustrate on the graph first. Again, I don't care about an accurate graph right now because that's really not the point. Just to make the connection of what's going on. The first equation ends up being a quadratic that opens up. The second equation is a line with a positive slope. These two, because one of them is a quadratic, can intersect in 2 points. Okay? I want to figure out both of those points. The method I'm going to use, though, is still going to be substitution. Okay? So right here on the second equation, if I were to add y to both sides and add 1, you would get this. Okay? There's the y in the first equation, so I would go back up there and say, all right, I have x squared plus 4x minus, I am able to put in 2x plus 1. Right? In the second equation, we rearrange things to show that that's the same thing as y. This would be minus 2x minus 1 equals 7. Or x squared plus 2x minus 8 equals 0. We end up with a quadratic, and this one is factorable. So I'd get negative 4 and 2. Okay, now this is why I wanted to show you the graph. This makes sense. Okay, we've got the x values for the 2 different points. We were expecting, from looking at that graph ahead of time, we got the expectation that we should get 2 solutions. Now I'm going to go back up to this one. I can use that, because now I have x values, and I can say, all right, 2 times negative 4 plus 1, well, that's negative 7. Now this, in your solution, you have to be really particular about that negative 7, that needs to be paired with the negative 4. Okay? That would probably be, my drawing is not to scale at all, but that would likely be that solution. That's the point where they intersect. And then I'll plug in 2. There we get 5. So then 2, 5 would be the other one. Okay, but I have to make sure that those x and y values get paired together, and then that's really clear in our solution. So here's another one. It's basically like the setup is really, really similar. It's not a word problem. One of the lines is one of the graphs is a quadratic, the other's a line. But I want you to be ready for this case, because it's a little bit of a... If I left you with the first one, I feel like you'd be thinking that, if it's a line and a quadratic, we should always get 2 solutions. Well, a better way to think about it is we'll get no more than 2. Okay? In some rare instances, we could get 1, but if we're looking for these points where it intersects, look at these 2 graphs. They don't. Right? The line, like here's the vertex of the quadratic. That's as high as it's ever going to get. And the line misses it altogether. Okay? I want to show you algebraically what would happen if that's the case. Okay? this first equation up here could be rearranged pretty quickly to 4 plus x. Okay? So then I go down to my second equation, and I'm looking right here. I get it down to a single variable, and it really looks like the one before where it's like, all right, we've got a quadratic. Subtract 3 from both sides and we would get plus 1, and there we go. Right? If you compare this to the one before, you'd be saying it's time to factor. But then you would notice that you can't. So we could go to our good old quadratic formula. Opposite of b plus or minus the square root of b squared minus 4. A is 1, c is 1. Now if you've used the quadratic formula enough, you might know at this point what you're looking for, which is that the number underneath the square root is negative, right? Which means we would have an imaginary component to our solutions. That right there right here, that's your red flag that graphically that this is the situation that's going on. All right? So if and we're really only going to be interested when we get to the graphical part. You know, we could go and you could keep simplifying that and get the imaginary solutions. But the stuff we're doing in Chapter 7, we're really only going to be concerned with the real ones. So if you see that square root with the negative, at that point you could just say no solution because you got a quadratic and a line that just miss each other altogether. All right, last two examples are what we'll refer to as break-even analysis that have some kind of application where typically a business one that we're looking for the point in time when the situation would either become profitable or seeing kind of two variables switch in terms of which is bigger. Okay. This is another tricky one where, notice it didn't give you any equations. So you got to write them. Okay. What we're after here is it's going to give us information for revenue based on how many shoes are produced and cost. And this is what we're after in this problem, is to figure out when is it, in terms of producing shoes, when is our revenue and our cost going to be the same. Okay? It's going to tell us like the minimum number of shoes we need to produce before this starts to become profitable. Okay? The paragraph does give us information about cost. Fixed cost of $300,000 plus it's another $5 for every pair of shoes that we produce. Revenue, we're going to sell them for $60. Okay? No fixed cost to go with that. Now this is kind of an interesting method to use substitution because that's really the technique that we're using. Go back to this. I've got the revenue and the cost equation now, so I need 300,000 plus 5x set equal to 60x. If I were to subtract 5x from both sides, I'll end up with that. And now I divide by 55. And this would be a round up. If you get a decimal, if I want to break even, I got to round up to the next whole number. But 5,455 pairs of shoes, I need to produce and sell that many. Once we hit that number, anything beyond that is going to be profit. This is really another break-even analysis, but it's not in terms of producing something, it's in terms of time. Okay? We have data on 2 different movies that are currently playing at a theater. And you can see here, they're both linear. And these linear equations give us, ticket sales in millions. Okay, so it's probably at multiple theaters. But the comedy, which maybe it's been out for longer, has, at the moment, a lot higher sales, but each week, people are still going to see it, but less and less. Its sales are going down. The drama, it's not nearly at the level that the comedy is right now, but maybe it's newer, people are liking it, its sales are going up. They both equal S. So what I'm after is to say, all right, 60 minus 8x, when is that going to equal 10 plus 4.5x? I'm going to move the constants over to the right side. Actually, let's put them over on the left. 60 minus 10. And then if I take the x terms and add them, I'll get 12.5. And it's coming together nicely. So I divide both sides by 12.5. And we will get our solution that the overall sales are going to change, at least it's our prediction, in about 4 weeks. We think the drama is going to be making more money each week than the comedy.